Okay, so what do we do? I have a picture here of the Great Leap Forward, and this is actually an anti-Obama an anti-Obama poster. You can see that Chairman Mao here has this Obama logo. I didn't know that. I didn't notice this in the beginning, but perhaps the Great Leap Forward is a prime example of a policy disaster. How some ideas about social progress were implemented very effectively throughout a huge country, and it had disastrous consequences. So this could perhaps be the first question. Okay, we might not be able to predict and to devise like the perfect rational policy from scratch, but perhaps we can avoid this kind of disasters. Okay, so one of the things that we can learn from, or that we can be inspired from, is experiments in contemporary medicine. The movement for evidence-based medicine is relatively new. It began, the modern evidence-based medicine began in the early 90s. And before then, it was very common that a treatment was accepted because it had been tradition to prescribe this treatment. A lot of trust was put in medical authority. That means, well, expert opinion, it was also called. And that was basically an old, often male doctor that said, we've been always doing this, and therefore it's safe to do it, or this is the best way to do it. And let me just give you an example of how horrible the consequences of this could be. In the 70s, there was this idea that if we treat women in the menopausal women with hormones, then we can delay the menopause or mitigate some of the effects, and we can improve their health and increase bone density and so on and so forth. So this was routinely prescribed to women all over the Western world, and it just went on. The prescription rate just increased year after year after year. So in the 90s, there were some doctors who wanted to test this hypothesis. Does it really work? What are the effects? And they were very criticized for making these tests. The critics said, we know this works because we've been doing this for 20 years. If it hadn't worked, we hadn't been doing this. It was like a circle argument. But they went ahead and did it, and it was under the guise of the World Health Organization. And they made a very large controlled study with thousands of women, and they showed that the alleged health benefits of hormone treatment were close to nil, and that hormone treatment caused breast cancer. It increased the probability that you would get breast cancer with as much as 20 to 25%. And you can compare this with, this is basically really bad. And just to give you a number, because we shouldn't talk about risks in relative numbers, but just to give you a figure about how much damage this caused, it is estimated that 200,000 excess people suffered from breast cancer in these 20 years, only in the United States. So the prescription of these hormones caused 200,000 cases of breast cancer in the United States. Doctors were killing their patients with the best intentions. And why? It's because they didn't know. They didn't know, and they didn't think that they needed evidence. They thought it was enough that some expert had a good idea. And it's the case that we have barely any evidence of what works today in social science. In many areas of society, similar numbers of people might be dying completely unnecessarily because we are not addressing the social problems as effectively as we could if we had the information about what works. So what did they do in medicine? Well, the idea was that when you introduce a new treatment, you need to, this treatment needs to pass a clinical trial where it's compared to a placebo or to the best existing medicine in the field for the same problem. And the thing with clinical trials is that they don't assume, they don't require a complete understanding of the human organism. They don't require that we have a theory that covers all cases and that explains why everything works. And that's why, for example, a lot of psychiatric treatments have been quite successful, even though we really don't know how they work. Of course, there are many psychiatric treatments that are not successful as well, and there's a lot of shenanigans going on with the pharmaceutical companies. But still, we can help people, even though we don't know exactly how this intervention works. And we can do this because the interventions that are being studied are directly action-guided. The medicine that we're testing on people is exactly the same medicine in the same dose that that we're going to prescribe in real life. And therefore it has a high level of relevance and a high level of action-guiding ability. It can really guide our actions because we know that this works. And the same thing could be made in a social, political setting. We can, for instance, like in this example, randomize different pedagogical techniques or randomize different randomize different ways of teaching students and observe what works. And we don't really need to have a complete theory of learning and how learning works to do these experiments and to learn from them. They can, so to speak, give us black box information. And I think that in the social sciences, where we have so little theory to lean on, this is particularly important. In the area of public health, this has already been tried for quite a while, and there's a really good track record of experiments. And public health is an interesting area because it's the intersection between public policy and medical science. And this is a trial of an anti-malarial drug that shows that the incidence of malaria. And it shows how we can create herd immunity in communities by distributing prophylaxis. Several of these large-scale studies have been made nowadays in public health, especially in developing countries. More of these studies could be made to see really what works. So what about theory? Am I suggesting that we should throw out dear old Adam Smith here and the rest of the theoreticians? Well, not really. This is not it. I've been like trashing social science and social science theories for a while. Let me talk in favor of them for a while. Theory can perhaps not give us the precise recommendations on what to do in policy. We cannot infer from economic theory what should be done to stimulate the economy in Sweden in particular. We need to take particular facts into consideration. But theory can provide us with useful hypotheses. Theory can say to us which hypotheses are worth testing. So therefore we know, for instance, that if we want to stimulate the Swedish economy, we should not, for instance, try to reduce the budget deficit. Because standard economic theory tells us that if an economy is depressed, then the government or someone else needs to spend and stimulate that economy. So we can eliminate some hypotheses. And this can help us prevent some policy disasters. But it's also the case that theory can show us how we can transfer the knowledge from one experiment to another. Theory can tell us if we have tried a specific job creation measure in Gothenburg. Will this work in Stockholm? We need to have some theoretical understanding of the similarities and differences between Gothenburg and Stockholm. And we need to know whether or not these similarities and differences are relevant for this particular experiment. And this is not something that we can, so to speak, to make an inference on whether or not something will work in another setting where the experiment was done needs this theoretical understanding. It's also the case that theories provide us with a decent prior, a prior probability of what will work. So if we had a study, a randomized control study, that said that homeopathy works great for depression, then we have a prior probability, a prior assessment of the probability of this claim to be true that is very low. Because according to our best theories about physics and biology and so on, and chemistry, we can infer that it's probably not going to be the case. So even if we have a successful experiment that shows that homeopathy works, we will be only shifting our probability a small bit. And our posterior probability, or our probability assessment after performing the experiment, or after taking the experiment into consideration, will still be very low, because our prior was so low. Any questions about this idea? Well, yeah, and let me just expand on that a little bit. My professor perhaps won't approve that I talk about Bayesian probabilities, or Bayesian statistics. But let me just tell you that this evidence-based paradigm requires that we think about what works, or think about claims, factual claims, in probabilistic terms. Rather than thinking homeopathy works, yes or no, you should ascribe each proposition, each claim about what works, a probability range. And this probability range can afterwards be updated in light of new evidence. Okay, I'm not going to go more into that, but check out Bayesian statistics, or Bayesian confirmation theory. Okay, so now perhaps perhaps to the most crucial question. How can engineers contribute? What is the special insight that you might have that social scientists often lack? Of course, one of them is just that you have an understanding of you have a quantitative thinking, an understanding of how to simulate and how to model behavior in a way that can help us understand human behavior and that we can use this to replace experiments in some cases. And I think this simulation is very nice because it shows us very counterintuitively that if we put a pillar in front of the exit, more people will be able to escape. I mean, intuitively, you would think that a pillar like this would make it more difficult for people to escape when there's a fire. But this modeling of human behavior shows that the escape is more structured, and therefore, from a fire safety perspective, it's preferable to have an obstacle at that point rather than not to have one. And this is, of course, something that needs certain proficiency with mathematical models and quantitative thinking. It's also the case that perhaps many of you will end up working in the IT industry or with IT-related workplaces where big data is used. And it's, to me, quite remarkable that the best social science in the world at this moment is not performed in university departments, but at large web service companies. And it has a lot to do with the incentives. I mean, if you are a professor of sociology at some department, well, you don't really have an incentive to make accurate predictions about human behavior in the future. You do have an incentive of formulating some really nice, grand, armchair philosophy about how theory is, you know, the great theory about how society is. And you don't have the tools and you don't have the incentives to test your theory or to make testable predictions. Whereas companies like Amazon and Google, they have a very, very strong incentive to understand human behavior, because that's what makes their companies profitable. And they also have the means, or they have acquired the means to devise theories and models about how humans behave, to be able to study them. Google makes more than 10,000 experiments a year. Many of them are very small, but they involve small tweakings in their web pages, in their interface, in the how information is presented, and so on and so forth. So they are performing lots more experiments than any social science department in the world. It's also the case that they gather lots of data that they can perform analysis on and find out a lot of things about their users, than any government or department can or university can gather. What if governments and government agencies had a fraction of this ambition? What if society took information as seriously as web companies do? What if politics was more about seeing what works, tweaking, making experiments, and continuously upgrading their institutions to fit what works best? Well, I think that this big data paradigm is slowly leaking into the public sphere. And perhaps Great Britain has been the most enthusiastic in adopting this view. New York also to some degree has started using data to devise policies and to continuously upgrade them. And I think that this could really help us a lot with avoiding the worst policy mistakes. And this is also a nice example that shows the Facebook connections of university students in Europe. And at least when it comes to university students, what's interesting about this graph, seems to me at least, is that you can hardly see national boundaries. And you see that connections between cities is much stronger than connections between different points in the same country. This seems to suggest that at least when it comes to university students and teachers, I think, the EU is in a sense a union of cities, not of nations. This is quite interesting. I'm not saying that we should exaggerate the significance or importance of this graph, but this kind of research can still inform our considerations. What about technology? I said a few minutes ago that technology is impossible to predict. We really don't know which energy sources are going to be the dominant in the next 20 years. Well, this is true in a sense, but it's also true that we can predict what's probably not going to be a dominant energy source. But this really requires a scientific understanding and an understanding of how technology works and what is technologically possible. Because sure, technology has many possibilities, but technology is also constrained by the laws of physics. And I think the CEO of Tesla Motors, Elon Musk, which is a very interesting person, and I think in many ways, he's a bit like an engineer superhero, in a sense. But he had an interesting argument that I think illustrates this point. And he said that even if we would make ethanol production from crops really, really efficient, so that we can extract, we can increase the amount of energy, incoming energy from the sun that is transformed into electrical energy, and as you can see, it requires quite a leap. It would still be much more efficient to burn this fuel at a centralized power plant and to deliver the electricity to electric cars, rather than to distribute the fuel directly, burn it in local combustion engines the way we think about doing today. And think about this. I mean, if you think about it, it's pretty logical, and it follows from just a very simple application of engineering and scientific principles. It's much more efficient to transport electricity than fuel. It's much more efficient to burn fuel in a power plant than to burn it in cars. And electric motors are much more efficient than combustion engines. And it's also the case that not even the most efficient crops, the crops that convert solar energy into chemical energy, are even close to the per area efficiency of solar panels. and discounting that crops also require lots of water and fertilizer and insecticide and so on and so forth. So just by looking at this simple picture from an engineering standpoint, you can inform a policy on what's going to be a likely fuel in the future for vehicles. Any questions on this? Yeah?
Yeah, the question I have is that you said that it helps people avoid mistakes.
Mm-hmm.
So we don't, I mean, we always use combustion in each vehicle. Why do you change the way we use it?
I'm sorry, I didn't get it. Could you repeat your question?
Well, you spoke about whether it's better to have general combustion and then spread the energy instead of having combustion for each vehicle, each
Mhm.
car. Then why not make it since it's what it's supposed to be made for?
Why these mistakes are made, or?
Yeah, exactly.
Well, because politics is not sufficiently informed. I mean, take the case. I'm not sure exactly how the political discourse about this is in the United States, but in Sweden, the political discourse around ethanol cars has been very disconnected from the scientific community or the scientific expertise. It's been a lobbying effort, and there's this group of, there's been a lot of powerful lobbyists that have been ramming through this issue. So it's been basically political discourse. And I think that, of course, politics is very complex. It's a very complex game, so to speak, and it's not easy to understand for people that stand outside of politics, which I do. I try to understand it, but it's really messy. But I do think that if engineers more actively participate in the public discourse on this topic, engineers can help inform politicians that this is really crazy. And there are, sadly enough, a lack of engineers in the political parties, in the political, among bureaucrats. There are just too few people who know how science and technology work. So I would say that it's a combination of two worlds being separated, perhaps by different cultures, perhaps by a mutual mistrust, but also a consequence of very fierce political lobbying from some interest groups. That's my best guess, but I'm really not an expert on the internal dynamics of politics. But, so that's just a guess. Scientists and engineers can also inform the public and public policy by explaining not only the boundaries or the limitations of technology, but also the boundaries and limitations of the climate and the systems where we inhabit. And I think you're probably familiar with this article or with this concept, natural boundaries concept. This was an article published in Nature a few years ago by Johan Rockström from the Stockholm Environment Institute. That was very cited and so on. And what's really interesting about this is that a bunch of scientists sat down and devised a very visual and intuitive model on the boundaries for humanity, at least in the short term. And what's interesting about this model, it's not, perhaps the boundaries are, that perhaps their information about the boundaries is wrong. I mean, I'm not endorsing that, but it's this idea that there are certain things, there are certain stresses that we can subject the environment to until a certain point. And after that point, then a danger, a risk of collapse becomes imminent. So here, as you can see, we are in the danger zone when it comes, according to Ross when it comes to biodiversity loss and the nitrogen cycle, and also climate change. And I think this way of thinking can really contribute to inform policy, because not only to say what's impossible, but also to say that within these boundaries, these things are possible. Because I think that in the social sciences we tend to think about social change and about technological change as linear, and that the possibility space of what can be done is constrained by an analysis of where we're today, and then we extrapolate from this analysis, like this. But by applying this boundaries thinking, scientists and engineers can tell us how much can inform us that within these boundaries there might be much more possibilities than we believe. So any questions about this? Okay. So what is engineering safety? A lot of you will end up working with complex systems. Might be airports, it might be power plants, it might be large factories, it might be the traffic system of a city, it might be the electrical grid, it might be something like that. And anyone who has been working with these systems know that they fail sometimes. And I think that this idea that failure is not only possible but also likely is perhaps the most important idea that engineers can convey to social scientists. And it's an important idea because we can start thinking about strategies when we fail, even though we don't know exactly what is going to fail. And one of these strategies is referred to as multiple barriers. And this is a picture of how, a proposed system to store spent nuclear fuel. And the idea here is to first encapsulate the fuel in copper cylinders. And the next step is to encapsulate these cylinders in bentonite clay. And the third step is to bury this in a very deep ground, very far away from groundwater, and under in a geologically stable area, and under certain sediments and layers of mineral. And the idea here is that every measure is sufficient to keep the radiation out from groundwater, from humans, or from people who might suffer from it. And by creating 3 separate and independent barriers, you can take into account the uncertainties involved in this project, and especially since we're dealing with a very long time span. The classical example of multiple barriers is, of course, the medieval fortress. As you probably all seen, historical films, movies, the typical medieval fortress had a moat, so the attackers would have to pass that barrier, so to speak. It often also had and of course larger walls with towers, and in the towers you had archers, and on the walls you had people with boiling oil to pour on people, and sometimes you had inner walls, and this was it was in Constantinople. They had many rings of walls. So the idea was that when the enemies crossed one wall, they would be stuck between the walls, and perhaps there was a lot of clay and mud, so it was very difficult to climb on the next wall because you didn't have your ladders. I mean, the ladders were very difficult to pull from one side to the other, and all the time you had people shooting arrows at you. So this is a typical example of multiple barriers, where each barrier is independent of each other, and where when each barrier in theory should be sufficient to stop an enemy. And this idea can of course be applied to social systems, to provide protection against war, against terrorism. You could think about the barriers concept in relation with climate change, where you think about multiple sufficient plans to safeguard the food production or other safety measures in the case of, for example, extreme weather and so on. Another engineering safety principle that is fairly obvious, perhaps to a lot of people, is this idea of safety factors. And a safety factor is the minimum allowed stress that a system is supposed to be subjected to, and the maximum stress that this system is. The maximum stress that is allowed and the maximum stress that the system can take. For example, we can imagine a bridge, and we have our calculations, and we say that this bridge can carry up to 10 tons of weight. And then we apply a safety factor of 10, and we say that 1 ton is the maximum acceptable weight or load that could be put on this bridge. And this is because, of course, we are uncertain about the conditions that this bridge will be tested. We don't know what weather it's going to be, how often it's going to be repaired. We don't know about potential earthquakes. We don't know about accidents that might undermine the bridge's integrity, and so on and so forth. And therefore, it's fairly obvious to someone who builds bridges or elevators or whatever that you cannot say that the maximum load should be maximum allowed load should be even close to the maximum load that an elevator can take or that a bridge can take. But sadly, this is how many economists and other social scientists seem to think. When we assess the riskiness of the banking system, we're not thinking in these terms. The capital reserves that banks typically have are not calculated with this safety factor in mind, not even after the Basel III rules. So I think this idea of a safety factor is essential in society, and it's an idea that should be incorporated in how we devise our systems. And of course, it's an expensive idea, and that's why it's seldom applied. But I think that's where these ideas from engineering safety needs to inform public policy. Social systems do fail. There is no such thing as a fail-safe device in engineering, and there's no such thing as a fail-safe system in the social sciences, and that's why we need safety factors. Fail-safe, yeah. The third system is a wordplay. I said just that there are no fail-safe systems, but we can make a safe fail system, and this is what you're seeing here. And the idea here is that if we apply the general idea that all systems will fail to some degree, then what we can do is that we can try to minimize the damage or the harm of a system failing. And this is the conceptual design of a passive safety nuclear reactor. So it's a nuclear reactor where when there's a critical shutdown of the reactor, the fuel rods automatically fall into cases with bore. Instead of the old systems, when there's a critical malfunction, then you have to manually lower control rods into the reactor that slow down the reaction. And of course, this is a big problem if you don't have electricity. And this was the case, for example, in Fukushima, where the electricity system was destroyed, or it was put out of. The earthquake disrupted the diesel generators and also the extra diesel generators, so they didn't have any electricity, and that's why they couldn't insert the control rods and cool down the reactor. But with a passive system, this reactor the harm would have been significantly limited. And this idea can also be applied to many systems in social science. We could, for example, have much larger food stockpiles in case of a catastrophic event, catastrophic collapse of important government functions. We could have an analog system of communication between important parts. We could spend money on keeping the analog system of communication working, so we could still communicate with each other if there was a major breakdown of the digital grid, and so on and so forth. So this is also an idea that I believe needs to be more rigorously applied in political systems and in political thinking. And I think where engineers have ample experience, but also a lot of ways of thinking around safety that can be applied to social systems. Any questions? Any thoughts about this? Okay, thank you so much. I'm going to write down the web address for